Namaskaram. Welcome to another video of GPU programming with Mojo. Today we shall explore a fascinating concept such as the GPU warp. A warp is the smallest unit of execution on a GPU, and it's nothing but a group of 32 threads executing a same instruction at the same time. Anytime you request any number of threads from a GPU, it will give you in batches of 32, expecting you to somehow arrange your data or algorithms in such a way to take advantage of this batch of 32. They are hardwired behind the scenes through shuffle bus, a special hardware wiring, so that they can talk to each other between those 32 threads without any explicit memory required. So this kind of avoids the fact of copying from one block, creating a shared memory, copying the data and reading from it. So it's a mechanism provided by the GPU alone to help us take advantage of this communication, intra-warp communication, which is very fast. Now think of it as people in a room. They can talk to each other because they're in the same room. They don't need specific phone lines or letters or email to be sent to them. They can just walk across the room and talk to them. If you were to talk to people in the other room, let's say you have a table in the hallway where you go and provide the information. Or if you have to talk to a person in another city, you have to actually send an email or post using the post office. So the post office here is the global memory. The table in the hallway is your shared memory, which is read by all the rooms in the apartment complex. And the people in your room where you can talk to is the warp. Obviously, there's only so many people you can put in the room, and hence the warp size is 32 and not beyond. So that should help you visualize how a warp or a group of threads are arranged. So in the GPU world, you can think of warping in two different contexts. One is at a thread level, where it executes the same instructions and takes advantage of SIMT, single instruction multiple data, at the register level. The one where we talked about, where it's single instruction multiple threads, where a group of 32 threads come together and perform the same operation. So let's dive into the implementation, and let's look at one of our earlier examples where we implemented a dot product and see how we can improve using the warp concept. Here we are taking 32 elements, vector A, multiplying with vector B, and computing the dot product. So without warp, the implementation looks like this, which we have explored in one of the earlier videos. We create a shared memory, we multiply it and produce the output of A and B and store it in shared memory. Then we use what's called as a binary tree reduction, where we use a stride of 4 and then 2 and then 1 and finally produce the output. If you want help visualizing how that looks like, you can use GPU Algo Visualizer to take a look at it. So it sort of goes like this, where you start from the first location, jump 4 locations and grab the fifth element, which is called a stride. Then the stride becomes 2 and finally the stride is 1, and the final result is stored in the first location, which is then returned back to the output vector. This is a very conducive algorithm to use warp. As you will see here, the first operation is multiplying A and B, and when you multiply A and B, you can also take advantage of the native SIMT concept that is available within Mojo, where instead of grabbing one element, you can grab 4 elements. So you grab 4 elements. This reduced add function uses SIMT behind the scenes, uses the SIMT width, which is 4 in my case, and grabs 4 elements and then computes the sum. So a set of 32 elements is now reduced to 8 elements of computed sum. But that's not the final product. You just shrunk from 32 to 8 by focusing 4 at a time. but still you will have to now take this 8 and compute the sum. You could just use a sum or what's called as a warp underscore sum. It's a primitive that is provided by Mojo, which takes advantage of the warp concept and computes the sum and crushes those 8 elements into 1. Now here it's one of the best practices used because you kind of use SIMT, which is single instruction multiple data at the thread level, crushing 32 elements into 8, and then this warp sort of crushes the 8 elements into 1. So in 2 lines of code with no shared memory, with no global memory, with no explicit copying, with no explicit algorithm conditions provided, you reduce the dot product of 32 elements into a single result output that you wanted. So that's the power of warp, which simplifies the code as well as gives you a performance speed up. So let's look at a visualizer for this and see how it shows up. Let me enlarge this. So before I click the buttons here, there is a variation where you could avoid SIMT, which is crushing that 32 into 8, and use warp on all of 32. Hard to say which one is better because SIMT is also sort of warping at the thread level, and the final 8 elements are crushed into a single element. So it's the performance benefit might be minimal, but in the event that you don't want to use SIMT, single instruction multiple data at the thread level, and avoid it, there is a variation in the code implementation which we'll talk about, where you can use warp on all 32 elements and compute the sum. So the first method is going 4 at a time, using only 8 elements because SIMT acts on 4 at a time, reducing the 32 elements into 8. Then you need only 8 lanes or 8 slots, which the warp executes and produces the output. But if you were to not to use SIMT, or let's say SIMT equals 1, you explicitly set SIMT equals 1 and purposely avoid using the 4 slots in the register, then it would look something like this, where you use 32 lanes, as it's called in the warp world, and execute all of them to produce the sum. Both are acceptable forms of programming and depends on use case which will yield better results, since both of them are taking advantage of the massive parallel processors that is provided by the GPU. So in Mojo, there are about 4 primitives provided out of the box: sum, prefix sum, shuffle index, shuffle down. These are the only 4 things provided for you to take advantage of the warp concept. Every slot in a warp is called a lane. So you can think of as lane 0, lane 1, lane 2, up to lane 31. So each slot is referred to as a lane in for a GPU warp. This implementation is a variation of the first, where you purposely reduce the SIMT width to 1 so as to avoid it altogether, and then use the warp sum on all 32 elements to compute the sum. We have to benchmark this and find out which one is faster, but both are again acceptable forms of programming. And just to touch upon this, element wise spins up threads in batches of 32. There is an inline function which has a load operation and explicitly set to 1 so as to avoid any taking advantage of SIMT width, which is 4 in my case. But all is to say that it is provided to the warp sum, which computes the grand total. These are just helpers to print the output. This is our setup to produce the input data. This is our traditional dot product giving us the answer 10,416. This is our simplified warp, where in just 4 lines of code we were able to parallelize at the SIMT level and at the SIMT level. This is the functional warp as it's called, where we purposely avoid SIMD, SIMD and take advantage of warp, specifically warp sum to produce the answer. Now, there's one curse for warp, which is the more if-else conditions you have, the more operations where you depend on your neighbors to be present or depend on the answers of your neighbors, the performance drop becomes very clear. If you go back to the rowing example, even if few of them go row in the opposite direction or stop rowing, the performance of the rowing team drastically reduces. So you have to keep that in mind when you use warp. It's not conducive for all algorithms, but in the event you could place it, it's highly beneficial for your GPU program. I hope this gives you a clear indication as to how warp works. Thanks for listening. See you in the next video.